binomial would have two terms, so it has the first term a and the second term b, and I raised it to some nth power. But then down here I actually chose a value for n. So here I raised it to the 0. Well, anything to the 0 is just 1, okay? Here I did a plus b to the first, which anything raised to the first is just itself, a plus b, okay? Here I did a plus b squared, so that's where I'd have to write it out like a plus b times a plus b, and I did all the work for you. I FOILed it out, a times a times b times a, b times b, and I combined all the like terms already. So you don't see all my math in the in-between, but that comes out to be a squared plus 2ab plus b squared. And then I did cubed, fourth, and fifth. So now I want you to talk with your groups about what are some patterns you're seeing when expanding the power of a binomial. What sorts of things are happening from row to row? Turn off the lights so you can see a little better. Kind of interesting pattern to show up.
There's that one more like number.
Oh my gosh.
One or something. Like the, I mean, like if you see the it's
first variable
the
and a lot of variables
and then the
are always just
exponent.
increasing
So
by
like
1 power.
a plus b
The key variable before that is increasing by 1 power.
plus
The one less power than the one on the far right.
Pascal's triangle, yeah.
More or less.
Starts as 1 and a plus b. And then 1, 2,
and then
1,
the
3,
second
1,
term
1, 4, 6, 1.
Yeah, it is Pascal's triangle. If you do the 2ab plus b squared, it's going to be 3ab squared.
And it's also just a circle triangle.
Yeah.
Or a right triangle.
Oh, how quiet. So let's share some patterns. What kind of patterns did you notice? Alex?
It's kind of Pascal's triangle.
Oh, yeah. What do you mean?
Well, with the 1 and then the A and the B, kind of are they don't necessarily equal 1, but they're going down, and then in the middle they're multiplied times 2, so it's A2B, A33B, A464B. So it's basically not like on the outside of the triangle, the ones, you put A on one side and then B on the other, and then in the middle you still have them variable, or not the variables, the coefficient.
Yes.
Coefficient equals the numbers inside of Pascal's triangle.
Okay, so you're kind of peeking at these things. So I'm going to say, like, you're looking at the coefficients to all these terms, and you're maybe like a little bit concerned about the n terms here, but what's the coefficient to a?
1. Oh, so it's...
And what's the coefficient to b?
1.
And what's the coefficient to a squared?
1.
And b squared. So are they actually all the coefficients from the numbers of Pascal's triangle? Oh, yes. Right? Okay, so you're looking at your green sheet and you're like, wait a minute. Those coefficients are all the numbers that we just looked at on good old Pascal's triangle. And I forgot to share my favorite fact about Mr. Pascal. His first name is Blaise. How cool.
Blaise Pascal.
Yeah, Blaise. But, I mean, come on. It's awesome. Right? Okay, so we're seeing the coefficients. Were there any other patterns? I mean, like, that probably popped out to everybody because we're like, whoa, Pascal's triangle. But any other patterns that you noticed? Delaney?
Okay, so like in the second term of a, the exponent of that is minus 1 of its coefficient.
Okay. So, like, even in this first one, this is a to the first. And you might be like, well, then a disappears. But what is the exponent to a then over here? It's a to the 0, because anything to the 0 is 1, right? So this is like a to the 0. It just canceled out and was 1. So then you look at the next line. It's a squared, a to the first, and a to the 0. And then it's a cubed, a squared, a to the first, and a to the 0. a to the fourth, a cubed, a squared, a to the first, a to the 0, and it just keeps going, right? Okay, did you notice any other patterns, Maddie?
So like for like the individual like variables, like in one where it's like a to the third, they all equal the exponent that was outside the parentheses. So then like when you have 3a to the second, if you add the two exponents together, it would be 3.
Okay, so now you're looking like, I'm going to look at this one where it's being cubed, because that's what you're talking about. You're saying this is b to the first, and now we have b squared, and then we have b cubed. And if I look at like the sum of the exponents in this row is always equaling 3, the power of the binomial. Okay, and that works like down here. Let's look at this one that has a power of 5. 5 plus 0 is 5. 4 plus 1 is 5. 3 plus 2. 2 plus 3. 1 plus 4. 0 plus 5. Okay, any others that you noticed? What's the one we could piggyback off of Delaney's? So Delaney told us about the blue ones, that the A's were going down. What's happening to the B's? They're going up. You don't see a B in the first one, right? So it must be B to the 0, and then it's B to the first, B squared, B cubed, B to the fourth. Okay? So basically what we're going to do is we're going to use this pattern, and we basically have all the parts we need. You're going to pick your coefficient from the row in Pascal's triangle. The row in Pascal's triangle will match the power of the binomial. So the fifth row in Pascal's triangle, remember the first one on the pyramid is really row 0, has the coefficients 1, 5, 10, 10, 5, 1. So we'll pick out those coefficients. And then we'll take the first term in the binomial, and it won't always be something like a, it could be like 2x. We'll take the first term in the binomial, and we'll raise it to the highest exponent, and then we'll go down by 1 for every term. And then we'll take the second term in the binomial, and we'll start it with the lowest exponent, which is 0, and we'll move it up by 1. So we have 3 parts to every term. Okay, the coefficient from Pascal's triangle, the first term, highest exponent going down, the second term, lowest exponent going up. Okay, so this is something that we can refer to in our notes 4.2 as binomial expansion. Okay, now remember I told you yesterday Pascal's triangle is like one of my favorite things. Not just because his first name is Blaze. Just because it's so cool. So Pascal's triangle is going to come back to us in second semester. When we learn about probability, we're going to see another way besides just patterns to generate the numbers in Pascal's triangle. Hi.
Is it no calculator today?
I don't care.
Okay.
What are you going to do?
I don't know. I just couldn't remember.
I can't remember what the test is. The test is calculator, right?
I don't know. I'll look.
Okay. But for right now, all we know is that we can generate the rows of Pascal's triangle, and we can come up with the coefficients. But like I said, in second semester, we'll get an addition to this formula. Right now, this is binomial expansion is really going to be by patterns. Alex's favorite. Now, AC, when we take those photos, you gotta promise to delete them if I got a weird look on my face. I'm not very photogenic.
I tend to
So I'm probably like in the middle of teaching and my face is like, you know,
I tend to try.
don't show anyone those photos. Just delete those. Okay, so if you take a plus b and raise it to the n, okay, these are the things that are going to be true by the patterns that we just discussed on the last slide. Your expanded polynomial will have n plus 1 terms. So like when we raise it to the first, we still had 2 terms. When we raised it, when we raised it to the third, then there were 4 terms. Okay. The coefficient for each term in the beginning is going to be the number from Pascal's triangle. Okay, so you'll have to say, like, which row is it? Remember, you can easily pick out the row because if you're cubing it, you're going to pick out the row that's after the 1 shows a 3. So it's going to be 1, 3, 3, 1. So when you cube it, you actually have 4 terms. Okay, and then A starts with the highest exponent, n, and then for each term you'll just drop the exponent on A. Until in the very last term, A will be raised to 0, which just equals 1, so it kind of disappears. Equals 1. And then B, the second term in your binomial, you'll raise that starting to the 0, the lowest exponent possible, and then it'll raise by 1 each time. It'll end on the n value. Okay, so we're going to do an example here together. We're going to do x minus 5 quantity cubed. X minus 5 quantity cubed. Okay, so remember, you need to figure out which row of Pascal's triangle you want. You're going to look at the power 3, the exponent, to tell you which row you want. You really want row 3 in Pascal's triangle, and remember the first row is row 0. So then we have our triangle of 1s, that's row 1. Okay. Here's row 2, and here's row 3. So how many terms will you have in your expanded polynomial? Look at how many numbers are in that row in Pascal's triangle. 4. So if you raise it to the third, you're going to have n plus 1 terms, which would be 3 plus 1. You're going to have 4 terms. So I'm going to break this up. I'm going to say like the first term, the second term, the third term, and the fourth term. And now I know the coefficient that would start off each term. So that'll be a 1, 3, 3, 1. Okay, so I'm in the end, I'm gonna be like adding or subtracting these terms. I'm gonna put them back as a polynomial. But right now I'm just gonna generate what the 4 terms should be.
Like the coefficients?
Well, those are the coefficients. Yeah, we take the coefficients from Pascal's triangle, right?
So like you're saying that the terms are like the coefficients for
The coefficients and the variables and the exponents. So now I have to go in. I've only picked out the coefficients from Pascal's triangle. Now I have to go in and I have to pick my first term, which is x, okay? And it starts by raising x to the highest exponent, right? Remember Delaney's pattern? A started with the highest exponent. So this is going to be x cubed, x squared, x to the first, and x to the 0. So I'm taking the first term in the binomial, raising it to the highest exponent, going down by 1. And then I take the second term, which is, be careful with this, what's your second term? A negative 5. You got to include its negative sign with it. Okay, so we're going to protect it with parentheses and we're going to put negative 5. But for the second term, remember the pattern I think Maddie gave us where our exponents always add up to the power? This one can't be raised to the third because then it would add to 6. This one starts at 0. Okay, the second term starts at the lowest exponent. Started at the lowest exponent and then increase it by 1. Okay, before I do anything else, do we need to clear up like where I chose those 3 things? Why I did what I did? Yes.
Well, like, okay, so is this focusing on the fourth row, and then like splitting it up by like let's say it was that 5 in like the fifth row of that triangle.
Yeah.
Is that what we're splitting it by?
Okay, so what I'm trying to do is like back here when it was just a simple a plus b. If it was being cubed, then the coefficients in that row, in that polynomial, would be the third row of Pascal's triangle. Because remember, this is row 0, row 1, row 2, row 3. Okay, so in the third row, I've got the coefficients 1, 3, 3, 1. Okay, so those are the coefficients for each term. And then you told me that the first term in the binomial, a, was going to be raised to the highest exponent 3, and then it would go down by 1. But now it's not a, it's x. So I've replaced it with x. Okay. And then we decided that, like looking at your pattern, that the b's were going the reverse. So the second term in the binomial, but notice it's supposed to be plus. So if you had like a minus 5, we're going to choose what is b really. B is really a negative 5. So we raise it to the 0, to the first, to the second, to the third. So we're just kind of replacing whatever a and b are, but we're still going to have those same coefficients from Pascal's triangle. Okay, does anybody else have any other questions they want to clarify on that one before I go on? Okay, the rest of it is just cleaning it up. Like you have to do the powers. Okay, so we know that anytime we raise something to the 0, it's going to equal 1, right? So the first term in the binomial or in the expansion is really just 1x cubed or x cubed. The next term is going to be 3 times x squared, and then we will multiply it by a negative 5, wouldn't we? Because negative 5 to the first is negative 5. So we have like 3x squared times negative 5. Well, what's 3 times negative 5? Negative 15. Okay. Then this is going to be 3x times negative 5 squared is a positive 25. 3 times 25 is 75x. And the last one, remember, anything raised to the 0 is 1. So this is 1 times whatever negative 5 to the third is. Negative 5 times negative 5 is positive 25, times a negative 5 is negative 125. So this equals negative 125. So I'm just like cleaning up what my 4 terms are. And then that allows me to say what the expansion for this will be. I can just write them back. X cubed minus 15x squared plus 75x minus 125.
How did you decide on doing the fourth row instead of another?
Because I'm going to keep saying it is actually the third row.
Oh.
Because remember in Pascal's triangle, the very first one is actually row 0. So row 1, row 2, row 3. So I kind of know that like row 3 is the one that has a 3 right after 1, right? Row 4 is the one that has a 4 right after 1. Okay? But the other way that I choose that is based on the power. So whatever your n is, okay, that's the row of Pascal's triangle that you want. So it's being raised to the third. So you want row 3, which this is row 0, row 1, row 2, row 3. Or you want the row, when you say row 3, you want the row that has a 3 right after 1. Okay, any other questions you want to ask? These are all really good questions. Okay, I'm going to do another one. This one's a little bit harder. Okay, but we'll see the pattern again. 3x plus 2 to the 4th. Quantity 3x plus 2 to the 4th. So which row in Pascal's triangle do you want? Row 4. Okay. That's the row that should start with a 4 right after the 1, right? We want row 4. Okay. And we, on the last example, we just used row 3. So I'm going to put row 3 right above it. Because you can generate Pascal's triangle. You know, like on a quiz, you'd only have to draw it out once. Then you'd have all the rows you need. Okay. So the coefficients are 1, 4, 6, 4, 1. How many terms will you have when you raise something to the 4th? 5 terms, because you always have n plus 1 terms. That's 4 plus 1. Okay, so you're going to have 5 terms. So I have my first term. I got my second, third, fourth, and 5th. Okay, they're going to start with the numbers from Pascal's. So we just put in the coefficients. 1, 4, 6, 4, 1. Then we take the first term. What's the first term in the binomial? 3x. Protect it by parentheses. And think about your patterns. The first term starts with which exponent? The highest or the lowest? Highest exponent. So we're going to start with 4, 3, 2, 1, 0. We know this one at the bottom, 3x to 0 is 1, right? Then take the second term. What's your second term? 2. In this case, we have a positive 2 because it's plus 2, so we don't need to worry about the negative. I just use parentheses to protect that term for my exponents in case I need it. And what's the pattern for the second term? Start at 0, the lowest. 0, 1, 2, 3, 4. Remember, you can always check that these two exponents should add up to 4 for all the terms. 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, 0 plus 4. And we know that 2 to the 0 is 1. Okay, here's why this one I would say is more difficult. You've got your coefficient of 1 from Pascal's triangle, and then you're taking 3x raised to the 4th. So that means you're really doing 3x times 3x times 3x times 3x. So 3 gets multiplied by itself 4 times. So you got to remember to distribute that exponent. 3 to the 4th is 81. X to the 4th times 1. So your first term is 81 x to the 4th. Next term, you've got your 4 from Pascal's. It's just there. Okay. And then what's it going to get multiplied by? Distribute your exponent of 3. 3 cubed is 3 times 3 times 3. 27. X cubed times 2. So now to get that coefficient, I have to do 4 times 27 and then times 2. So that's what? 108 times 2. Is it 216? 216. Okay, next one. 6 times. What value? 9x squared. Don't forget to square the 3, right? 9x squared times 4. That's what? 54 times 4. 216 again? 216x squared. Okay. Next one. 4 times, now it's just 3x to the first. That's just 3x, right? So we got a 12x. Times 8, and 12 times 8, 96, x. And the last one is just 1 times 1 times 2 to the 4th, which is 16. So I found all 5 terms. 81x to the 4th plus 216x cubed plus 216x squared plus 96x plus 16. There's my expanded polynomial. Yes, ma'am.
Is binomial expansion then basically just getting a polynomial into standard form?
Yes, binomial expansion. So like what we're actually doing here is like if you have 3x plus 2 to the 4th, if you expand that, then you write it out. 3x plus 2 times 3x plus 2 times 3x plus 2 times 3x plus 2. And this is a faster way. Pascal's triangle and the pattern binomial expansion is faster than like multiplying these two and multiplying these two, and then you still have to multiply your answers again. Okay, Alex.
So I think I figured out another pattern.
Yes.
With 3x plus 2 quantity to the power of 4, and then x minus 5 quantity cubed, I've noticed that if you add the exponent's number, that's how many terms there are.
Yes. Wait, what do you mean the exponent's number?
The exponent for quantity to the power of that exponent. If you add 1, there's 5 terms there. So
yes, exactly. There's always an extra term to your power, right?
Yeah.
Excellent. I agree. Okay. All right. Any other questions? All right. So that's like the hard part about your homework is like understanding this new binomial expansion with Pascal's and like the patterns. So if you see something like this where it's a binomial being raised to a power, you can go ahead and use Pascal's to expand. You are going to have some other questions on the homework, but I'm thinking you're going to be able to do these. Okay? So you don't have to write these down in your notes. But what would you do to add 2 polynomials that look like this? Would I distribute? Yeah, if I'm adding right here, it's a matter of combining like terms. When are you going to distribute? When it's multiplication, when like the parentheses are right next to each other, right? So like I could do this real fast. That's 4x squared minus 3x minus 4. Watch your signs, right? What would you have to be careful of? Try not to pack up just yet because we have 5 minutes, but you don't have to write this down, but I do want you to pay attention. What would you need to be careful of if you were subtracting polynomials? Yeah, on that last polynomial, because you have multiple terms back there, I always say like you should distribute your negative. I'll be real honest and say the best thing you can do is change it to adding the opposite. So before you ever start the problem, don't leave it as subtraction. Make it a plus, and then change all of these signs. So this is negative, positive, negative. The people who don't do that often do the wrong signs for x and 7. And that just gets really frustrating because you're never getting the right answer. So you can change it into an addition problem. That just means everything behind the subtraction changes its sign. Okay. So then I would go through and combine like terms. Like in this one I have a 3x cubed. It doesn't have a like term. So I just have 3x cubed. And then I have what? Negative 4x squared plus 2x and minus 8. Just combining the like terms. Okay. Okay, and then this would be a case where you would do what? Distribute. Okay, when you multiply, let's just review from Algebra 1. When you multiply 2x squared times x cubed, what do you get? You add your exponents. So you'll get 2x to the 5th. And then 4x to the 4th. And negative 6x squared. Okay. And I think I have a more complicated example where you have more than just a monomial. Still, what would you do? Just distribute, right? This one says multiply, so then you should distribute. On your homework, if it's add and subtract, don't distribute. You're doing a lot more work than you need to. Okay, combine like terms. So in this problem, you would start by distributing your x cubed. I always, when I'm doing my distributions, I do like my first set. Okay. And then what I like to do with this distribution when I distribute the negative 2x is I write it on the next line and I put like terms in columns. So like negative 2x times x squared is negative 2x cubed. So then I know those two terms get put together. If you just keep writing it, then you have to like keep track of all your terms. That gets a little bit messy, but this will be a little bit nicer. And then I can do the same thing when I distribute the 1. So I'll get plus 1x squared minus 3x and plus 3. Okay, so at the very end of that, I would go through and combine all my like terms. X to the 5th minus 3x to the 4th plus x cubed plus 7x squared minus 9x plus 3. Okay, you can't use Pascal's triangle to multiply polynomials unless it's a binomial that's being raised to the power. So it's like the same thing times itself over and over again. Okay? Now, if you need more examples of adding, subtracting, multiplying as you're doing your homework over the weekend, you can rewatch the video, this last part, and like take notes to go into your notebook. You can also look in the textbook in that section and maybe like copy down a few of the examples that they do. Bummer. Okay. There are also some special patterns that some of you may be aware of for multiplying, like a minus b quantity squared, a plus b quantity squared, a plus b times a minus b. And those are real handy, but you don't have to memorize those. You can always just like distribute and combine like terms and you'll get to that answer. Okay? But I use this in pre-calc a lot, so I know those patterns. It makes my life easier. Okay, and your homework. You know, it looks like a lot of problems compared to some of our other homeworks, but think about there's like a couple adding and subtracting. Those aren't going to take very long. Okay, and you're going to have a concept check on Monday. So I'm going to ask you things like end behaviors, y-intercepts, make a table of values, graph a polynomial, and also our polynomial operations are fair game for that. Okay? You guys did a great job. Okay. Make sure you practice on your homework so you don't forget all the patterns that we discussed today over the weekend.